Lab program 7. From a given vertex in a weighted connected graph, find shortest path to other vertices using Dijkstra's algorithm. Write the program in Java. So this program is basically to implement the Dijkstra's algorithm, which we have seen for single source shortest paths. So a predominant algorithm in this category. So here we have seen by solving an example by considering this graph that the tree vertices, remaining vertices, and illustration that for every vertex that is present in the tree vertex, we have to find the minimum cost edge to all the remaining vertices, and we have to pick the one which is minimum for the next iteration, and we have to continue like this. And as we can see, the algorithm, so for every vertex, v in v, so initially all the distances are assigned to infinite. Okay. And then initially the set of vertices is null, and then for I equals 0 to v minus 1, we have to delete the minimum priority element. I mean, we have to pick the edge with the minimum cost added to the vt, and then for every vertex u in v minus vt, I mean for in the remaining vertices which is adjacent to u star. Okay. So in the example, say for example, for this iteration we have chosen b. So from b, which are all the adjacent vertices, it is a, c, and d. So for these vertices we have to identify such a such a vertex for which the cost is less, the total cost starting from the source, and that is what in the algorithm. So if du, so distance to this u star plus the cost from u star to u, if it is less than the current distance, then we have to update, the distance. Okay. So in order to better understand the implementation, then solve at least for two graph examples with the different, considering the different vertices as the source vertices. So in this case we have considered the vertex a as the source vertex. Okay. We shall look at the program. Yeah. So starting with the main function. So int cost. So this int cost, entering the number of nodes, and then entering inputting the cost matrix is the same for Prince, Kruskal's, and Dijkstra's. So this code remains same. So you can see we are inputting the cost matrix, I mean the adjacency matrix representation of a graph in the two-dimensional array cost. Okay. Then we are calling the method Dijkstra by passing this cost matrix and by passing the source vertex, in which case it is 0. The first vertex marked as 0 is the source vertex. So if you would like to have a different source vertex from which you have to find the single source shortest path, you have to modify at this place. So now we'll go to the Dijkstra method. Yeah, the Dijkstra method. So in the Dijkstra method, there are a few data structures which we are using. First one is the array distance. The array distance, which is used to hold the shortest distance from source node to the I node. I mean for every other destination nodes. Then one more array of type boolean. I mean the elements in this array are either true or false, which is used to set true if the shortest distance from source to I is finalized. So if the shortest distance to a particular vertex, particular destination vertex is finalized, then it is set true, otherwise it is false. Next. So initially we can see the algorithm, we are initializing like this. So distances are initially infinite. Okay. And so that is what distance is set to infinite, represented by 99 in our case. So initialize all distances as infinite, and shortest path from source to I are all false initially, are all false. Next, the distance from source vertex to itself is nothing but 0, and hence we just update one entry in the distance array of source is equal to 0. Okay, because the distance from a vertex source to itself is nothing but 0. Next, to find the shortest path for all other vertices, what we have to do? So int count is equal to 0, count less than v minus 1. You can see the algorithm for I equals 0 to number of vertices minus 1, exactly the same thing. Okay, so int count is equal to 0, count less than v minus 1, count plus plus. So int u is equal to minimum distance. So here we have written one more method for picking the minimum distance vertex from the set of vertices which are not yet processed. Okay, so there are vertices, I mean we have to pick such a vertex, okay, from the set of remaining vertices which is not yet processed. So in the example we can see, so in the first iteration it is b a comma 3, c infinity, d a comma 7, e infinity. So among these remaining vertices, which one we chose? It is b a comma 3, which is the minimum one. The same thing is being done in this logic. That is, we are picking the minimum distance vertex from the set of vertices which are not yet processed. Okay, so these are the vertices which are not yet processed, out of which we have to pick the minimum one. Therefore, so we pass the distance and we pass the path arrays, the integer array and the boolean array, to this method minimum distance. So now we will see what this minimum distance, how it works. So the minimum distance method, so it takes the distance and the boolean path as the arguments. Then min is equal to 99, minimum index is minus 1. So these are the initialized values. So now we have to pick the minimum distance one. So that is why we have to scan all the indices, right? So if the path to v equals false, I mean the vertex should not be processed and the distance to that v should be less than or equal to minimum. So if that is the case, make it as minimum, and minimum index is nothing but v. So that is what we will be returning, that is the minimum index. Okay, so when you return the minimum index, what does this represent? The minimum index represent the set of remaining vertices, right? I mean we are choosing such a vertex to which the cost is less. So that is the meaning of minimum index. Okay, so now we come here, minimum distance comma path. So now u we get, so path to u had to be set to true. Okay, so mark the picked vertex as processed, because this is the one we are about to use for further processing. So that is why we have to mark it as being processed. Okay, right. Next, here is the main logic. You can see the algorithm. So here is the main logic. Now we have chosen u star, right? So for every vertex u in v minus vt, I mean in the remaining vertices which are adjacent to u star, so currently we have picked one vertex, that is u star. So we have to find all the adjacent vertices and we have to check whether the distance to distance from source to u star plus cost from u star to the new destination, if it is less than the distance from the source to u, then we have to update it. So the meaning is apparent here. So here we have to update the distance value of the adjacent vertices of the picked vertex, and how we are supposed to do. So here there are 4 conditions, you can see there are 4 conditions. Okay, the meanings are very simple. So we have to update the distance right? So we have to update the distance to a particular destination v only if it is not in the path, right? I mean only if it is not yet processed, right? So that is why the first indicates not yet processed, I mean not of path of v, right? So if it is set to false, so not of false is true, so we have to choose such a vertex. So that's the meaning. Okay, so if the vertex that you are considering is already processed, then there is no point. So that is why not of path of v means not of false is nothing but true. Okay, so only if it is not in the path. Okay, and next is that there should exist an edge from u to v. Okay, so if there is no edge that exists, uh, then it will be marked as 0, especially from vertex to itself is usually 0. So that is why there should be an edge. So graph of uv. Okay, so this graph is not, I mean the adjacency matrix, there is a distance from u to v which is non-zero. I mean there exists an edge. Okay, it should not be processed and there should be an edge from u to v. So this is what, see here, for every vertex u in v minus vt which is adjacent to u star. How do you identify a vertex which is adjacent to u star? By noting down, right, by verifying in the adjacency matrix representation, is there any edge from u to v, right? So adjacency matrix u to v not equal to 0, I mean there is an edge from u to v. Next, and the distance to u is not 99, I mean it is not an infinite. Okay, and the total weight of the path from source to v through v is smaller than the current value of distance to v. So what this distance array represents is that for this index v, right, it represents the minimum distance from the source, all the way from the source to the vertex v. So what we are doing is, right now we are considering u, therefore the shortest distance from source to u plus the distance from u to v, if you are adding these two and if it is less than the currently existing value, that is distance from source to v, then we have to update it. So we can see here in the example, one example we can see here. Yeah, so in the first iteration d a comma 7 was there. Next, when we considered b a comma 3, next for the remaining vertices we are updating d. So when we are updating d, so d is reachable with source, from along the source, right? So source to b, from a to b the distance is 3, and from b to d the distance is 2, right? B to d distance is 2 and the total cost is 5. What was the earlier cost? 7. So this earlier value 7 is represented here, distance of v. Okay, and what is this distance to u? So distance to u is nothing but 3, and the new edge, that is u to v, is nothing but 2, the new edge. And if the total weight is less than the currently existing value, then update for distance to v as the same thing. So distance to u plus graph of uv, right? So 3 plus 2, so which is nothing but distance to u plus edge cost from u to v. So that is how we have to update it. So that is why, so this is the main logic which you need to understand in this algorithm. So we have to update a distance to a particular destination vertex only if it is not yet processed, and if there exists an edge from u to v, I mean which is an adjacent to u, and the total weight from source to v through u is smaller than the uh, currently existing value from source to v. Okay, so if that is the case, we have to update the distance to v. Okay, So this is the important logic in this algorithm. Okay, so that's it, right? So we are processing it for v minus 1 number of iterations. We are done. Okay, and finally print. So source vertex is source, then destination vertex distance. We are just printing out these distances I and distance. Okay, and one more thing to note in this program is the variable v. Since the variable v is accessed across all the methods, and how these methods are usually declared as static. I mean, they can be used without instantiating. The same thing holds good for this v also. So if you can just remove this static and if you just use int v, you will get the error like this, that the non-static variable v cannot be referenced from a static context. Okay, so that is why we have to make it as static, so that without instantiating, right, we can use the members of the class. So that is one thing to note down. Yeah, right. So that's about this program, and let us look at the output. So enter the number of nodes. So I will input the same graph. So there are 5 nodes, so value 5 I will enter the cost matrix. So I will be entering the cost matrix. Yeah, so the source vertex is 0, destination vertex and the corresponding distance from source. So 0 to 0, 0, right? Next 0 to 1, what is the total cost? 3. Is it so? 0 to 1, I mean from A to B, the total cost is 3. Next to 2, what is the total cost? 7, right? So here C. So to the destination C, what is the total cost? 3. Next, for the destination D, what is the total cost? 5. For the destination D, which is nothing but 3. Destination 4, I mean the vertex E, cost is 9. Vertex E cost is 9 from the source. So that is how the single source shortest path. So while taking the output, initially draw the graph, solve it manually from a particular source vertex, take the output, and do it for at least 2 graphs with the 2 different starting vertices. Thank you.